Okay, so now we're moving on to section 4.6, variation of parameters. Remember, we're skipping 4.5 because it's basically just the method of undetermined coefficients using a slightly different approach. So, if you know method of undetermined coefficients from 4.4, that's good enough. So now there's two problems with the method of undetermined coefficients, one of which is that the equation must have constant coefficients, and up until now they always have. Well, for the most part they have. From section 4.3, all those equations that you solved had constant coefficients. We'll see later some special cases where they don't have to be constants, right? Where they can be of this form down here, where the coefficients, if you will, of the derivatives might be just functions of x, like sine x or log x or something like that. But in general, at least for now, they're going to be constant coefficients, like they are here, right? So let's stick with second order equations, right? So no derivatives higher than 2. And because you know how to find the complementary solution, right? Okay. So if the coefficients are not just constants, this is fine. But the thing is, you can always divide by a2 on both sides, and so when you do that, you get something like this form here. And so this is the form we're going to be looking at. Okay. So also non-homogeneous, right? So you have the right side is now f of x, which is really just g of x divided by a sub 2, right? So, yeah. All right. So depending on p and q, we may or may not be able to find the complementary solution. But if they're just constants, we can always find the complementary solution. Now the question is, how do we find a particular solution, right? So again, well, that depends on the g of x, or in this case now, f of x. So just as an example, suppose that your f of x is, say, tangent x, right? So the problem is the method of undetermined coefficients won't work for tangent x. You might think, well, just do a times tangent x. But that doesn't work. And part of the reason is because when you take derivatives of this, it doesn't just involve tangent anymore. It involves secant squared. And then the second derivative will be something like 2 secant squared times tangent. And it's going to be a mess. It's just not going to work, right? The same thing would be true if you have just, say, log x, or something even weirder, like e to the negative sine squared of x. So any of these functions, method of undetermined coefficients, just won't work, right? So when this f of x is some function that doesn't fit the exponentials, polynomials, or sines and cosines, then you're in trouble. Undetermined coefficients won't work. So variation of parameters will take care of that. In fact, variation of parameters will work even when you can use the method of undetermined coefficients. However, as you'll see in a little bit, it may not be the easiest way. Right? All right. So the idea is that whatever this f of x is here, to find our particular solution, we're actually going to, so we already found the complementary solution. We have the fundamental set of solutions, the y1 and the y2. Now, to form the particular solution, we're going to assume that it's something of this form right here, right? That our yp is going to be not just c1 times y1 and c2 times y2. It's going to be some function of x, which we can call c1 of x, but just so we don't confused with constants here, this is going to be some function u1 of x times y1 of x, plus u2 of x times y2 of x, right? So we're assuming that the particular solution will be of this form. Okay, so so now when we plug this into, well, say this equation here, so you have to take not just the first derivative, but the second derivative. And of course, that's going to be a little sticky here because that involves the product rule. And so we're going to dispense with the u1 of x. We know that u1 and y1, u2 and y2 are functions of x, right? So when you take the first derivative, well, here's what you get, right? Using the product rule. And so then taking the second derivative, you get something even more elaborate, right? So plugging both of these, right, that's our, right, y double prime, y prime. If we plug these back into this equation here, well, after a little bit of algebra, this is what you're going to get, right? And it's on 2 lines here, so make a note of that. Okay, so what happens is that this form here and this form here, the y1 double prime plus p y1 prime plus qy1, we're assuming that that the y1 and the y2s are complementary solutions, right? In other words, they solve the homogeneous equation, right? So that's what makes these 0, right? So in fact, this and this term end up being 0, right? Because they solve this equation here, right? So now, right, so you sort of reverse the product rule and you get the following derivative here, right? So this reduces down to this equation here. The idea now is to take this piece, which is the same as this piece, these these have to be equal to 0, and then this piece here, the derivative of this, should be equal to the f of x. Why? Because it works. I mean, there's nothing deep going on here. It's like just pick these equal to 0 and this equal to f of x, and it should work. And you get your system of 2 equations and 2 variables here, right? The 2 variables here being u1 and u2. That's what we're solving for. And you notice we don't even have that here. We have u1 prime and u2 prime. So let's solve for those first, right? So we have a system of 2 equations and 2 variables. In fact, if you want, I can write that system down here. The first equation is u1 prime y1 plus u2 prime y2 equals 0. And then the second equation is u1 prime y1 prime plus u2 prime y2 prime equals f of x. And you solve this system for u1 prime and u2 prime. Sorry, 2 prime. And, well, in general, you could just use Cramer's rule, right? So when you use Cramer's rule, you get these solutions for u1 prime and u2 prime here, right? So these are the solutions we're going to look at here. And so what is W? W is the usual Wronskian. Remember the Wronskian? Right, so you just form the 2 by 2 determinant with y1 and y2, the fundamental set of solutions, and then the second row is their derivatives. There's W1 and W2. These are going to be, again, from Cramer's rule, you get this. But since one of the elements of the matrix here is 0, you get a very simple thing. It's just negative y2 times f of x and y1 times f of x for W2. So you get this, right? And right, so those are y1 and y1 prime and y2 prime. Then you have to integrate those, and that's what's happening down here. Is we're just writing down the solution y of x in terms of the complementary part, and then the particular part, which is this mess here. So the main thing I want you to realize is that you can go through this process, every example you're going to do or every exercise you're going to do in the homework. I would not. I would not do it that way because it just takes forever, and it's not necessary, right? We've done it once, sort of, and you don't have to do it again. Certainly not for every example, right? So the main thing that you should be looking at here is this solution. You can think of this as essentially a formula now, right? You have your y of x. You're solving this equation up here, y2 y double prime plus p of x y prime plus q of x y equals f of x. And right, once you get your fundamental set, your complementary function for your solutions, this gives you the complementary part, and this gives you the particular solution. And just think of it as a formula, right? So up until now, the book would always say, well, don't memorize the formula, remember the method. In this case, I think the method is just too cumbersome to try to do for every exercise, right? Maybe just do the first one like that, but I wouldn't. I would just use this formula here from now on. So when they say solve a problem by variation of parameters, it means using this formula here. So, right, so this is something, well, I have in my notes that this is something that you should commit to memory. Obviously, you don't have to do that. In any example, of course, you can always look it up, and on any test, I will just give you the formula. There's no reason to even memorize all that. So that's even better, right? You don't have to remember the whole method, and you don't even have to remember the formula. You just have to be able to apply it. And, and that's not trivial either. You have to calculate the Wronskian, you have to calculate these, and you have to be able to calculate these integrals. And keep in mind that, right, depending on what f is and what the Wronskian is and what, y1 and y2 are, these integrals may not even be integrable. They may not be doable, if you get, the integral of e to the x squared, for example, you're not going to be able to, or in this case, e to the t squared, right? You're not going to be able to find an actual, fundamental answer in terms of sines, cosines, logs, all that stuff. So you just may have to be satisfied with leaving it as an integral. And, if you really need to find let's say a solution for x equals 8 or whatever x is, these become definite integrals, and then you can just use an approximation scheme to approximate these integrals at a particular value of x. So with that, I think one more thing, right? So in most of the problems, you will be able to evaluate these integrals. It's as long as you remember all your Calc 2 integrals. What was I going to say? I forgot. I forgot what I was going to say here. So I think I'll leave it at that, right? It's just, we're going to look at some examples of this, just using this formula. Oh, yes, the one thing I wanted to mention was the 0 down here, right? This could be any number. Essentially, we just want to get the general antiderivatives of these. So whether you use 0 or 1, it doesn't really matter. We're going to ignore the constants there. They just don't come into play. So I think the book uses x0 as your lower limit of the integral here, but it's really just the x we're going to worry about. And remember, these are integrals with respect to t. X becomes the variable after which you integrate these. You're going to get a function of x. The t will be eliminated. The t is a dummy variable, right? So I think that's all I wanted to say for now. So I'll leave it at that.